Test. Can you hear me for people who are online? Okay. All right, good morning. Let's get started and we'll continue on the unit step function. We'll quickly finish that. Probably is 1 or 2 example. And then we'll get on to a new topic, a new type of function, which is called impulse function today. Okay. A quick review, we have defined ourselves a new function called the unit step function. Okay, which is defined as 0 when t is less than 0 and 1 when t is greater than 0. And there are many usefulness for this unit step function. At the end of the particularly at the end of the lecture, I showed you, a couple of applications how you can write a piecewise function using the unit step function by expressing it as a single expression, right? So I bring up an idea called cookie cutter. So cookie cutter basically means it really depends on how you're cutting things. I mean, this unit step function is a cookie cutter all the way infinitely to the right, right? So you could multiply this u of t with any other function, then you're cutting off anything on the left side, right? You're only leaving the function's value on the right side. So that's a cookie cutter concept. We also have demonstrated, for example, you could have a cookie cutter anywhere. So let's say 1 and 2 over here. Then this is a u of a t minus 1 and minus u of a t minus 2. Right? So now you create yourself a different cookie cutter. Right? So I mean, maybe let me show you one more example right here. So let's say I have a function f of a t. So this is a triangle function, not a very regular triangle. There's an incline a little bit. So it consists of basically 2 straight lines. The first part of this, and then the second part of this straight line. All right, so you could definitely find out, okay, what is the line equation? I mean, this is a part of this straight line equation, and this is a part of this straight line equation. All right, so there are 2 straight lines. And this green one here, of course, is t. Okay, that's a straight line t. And this black one here, if you wanted to plot this, find the line equation for this part here, if you have 2 points, you can create this line equation. Okay, so this is a -2 t minus 3. So this line is -2 times t minus 3. So you got 2 straight lines, but f of t is just part of it, right? So then if you write this f of t using piecewise notation, then you have to write, okay, for t between 0 and 2, the function equal to t. And for t between 2 and 3, the function equal to this. And every other value of t, the function equal to 0. That's how you would write it using piecewise notation. But now let's see, if I want to say, okay, how can I write it? Just using one single expression by making use of unit step function and the concept of cookie cutter at here. Okay. So you look at the first one. This is a portion, the first curve. Which part are you cutting out? Right, you're cutting out everything. You're only leaving this portion here. Right. So then I can multiply this t with a certain cookie cutter within this range at here. So that will be u of t minus u of t minus 2. So whatever's in the bracket, this portion here, give me a cookie cutter and multiply this with the original t. You're left with just whatever inside the cookie cutter. And the second portion, right, is this portion here. So plus, I mean, this is supposed it's negative, but anyway, so let's just -2 of t minus 3. Right, that's the second part of the straight line. Which part are you cutting out? You're leaving out only the portion between 2 and 3, right? So what should I do? U of t minus what? 2, exactly. And then minus u of t, 3. Okay. Yes. I mean, minus, plus, positive, minus, or minus. Yeah. I'm trying to be a little consistent with this one here. Basically, this is the equation for that straight line. Right. Okay, so make best use of this sort of a concept, right? You can simplify your writing of the function f of t. In this week's tutorial, you will see that when we do convolution of two piecewise functions, you certainly can do it graphically, but for every part of the graph, you can also express that using one single expression by involving the unit step function. All right, so one more example about unit step function, okay? And then we can move on. So for this example, let's look at what is the convolution between an arbitrary function f and unit step function u. So let's try this. Okay. Let's assume f of t is causal. Okay, so now I'm going to write down the definition of convolution first. Definition convolution, right? It's f of t a convolute to g of t, but of course right now g of t is being replaced by the unit step function. So according to the definition, it's f of a tau, and then times, it's supposed to be g, but now it's a u, and then t minus tau d tau. Okay, so I mean, by just looking at this, it's hard to tell, you know, what's going to happen next, right? So let's try the graphic approach a little bit, and then we'll see. I mean, for this term here, this u of t minus tau. How do we get this u of t minus tau? If you recall graphically, we first from u of t to u of tau, then from u of tau to u of negative tau, and then from u of negative tau to u of negative tau minus t. That's how you can arrive at this u of t minus tau. And graphically, right? So let's start from this u of tau here. So u of tau give you the typical unit step function. Of course, now it's in terms of variable tau, and u of the negative tau give you a flipped, mirrored version of that. Then next one is a shifted version of it. And you're shifting this graph to the right by amount of a t. So once you shift to the amount of right by amount of t, this edge at here becomes t. This is still 1, right? So this is u of t minus tau. Okay, so that's what u of t minus tau looks like, okay, based on the graphical procedures. And the convolution, what you're doing is you're multiplying this f of a tau, okay, with this function on the graph at here. Of course, we're not given what this function. So whatever the function looks like, right? Yeah. So you're multiplying the red with any curves showing up here. So principally, use the concept of cookie cutter. You are going to multiply. You look for the overlap. So the overlap happens, right, only between this range. Because other than this range, when you multiply the two functions together, you should end up with 0, right? So then back to this integral here. Back to the integral here. So the integral, your integration, right? The two questions we ask about. The first question, where does the overlap happen, right? And what is the range of the t? But of course, this range of t here is pretty obvious. The t has to be greater than 0. So it happens between 0 and a t. So the integral limit is 0 and a t, which is great. And f of tau, you know, we don't know what it is, but we just keep it as f of a tau here. But then this value is 1 and d tau. So you end up with just a 0 to t and f of tau d tau. So if you have the function f, then you can integrate and you can get a result. Right? So technically speaking, if you look at, so what does convolution between arbitrary function f and a unit step function u give us? It gives you this integral at here. And what is this integral then, right? I mean, if you have a curve f of a t, right, and this integrals from 0 to t, so it didn't specify. Maybe the t is anywhere 2 or 3, whatever, right? So basically, what you're getting is the area underneath the curve between 0 and t. So that's the conclusion. If you convolute your function with u of t, then you're getting the area underneath the function between 0 and t. That's the conclusion. Okay, so that's actually sometimes we probably make use of the results in part of the question in the future. So any questions on unit step function? Okay. There was a student asked a question, what is the point of a unit step function? If I can graph a function with a piecewise concept, I can probably even better visualize that using a piecewise concept, right? But once you introduce this u of t as a symbol and writing everything entangled with the u of t there, it's actually making it a little more confusing, right? Which I totally agree. Anyway, the point here is it's not that just because this, then u of t is not necessary anymore. It's a math tool, right? So there are other places, there are other situations you can certainly still use it. You can make your mathematical expression more efficient. Okay. I don't argue that just by looking at it, it's not as straightforward as a drawing or as straightforward as writing a piecewise information. Okay, so now let's introduce the second important kind of function called impulse function. And this function is denoted using delta t. So the Greek letter, small letter delta. So this is how you can write a delta. This is how I write a delta, right? So delta t. Just like the unit step function, the symbol for that is dedicated to u, and then impulse function, the symbol for that is dedicated as a delta. First of all, what is definition? Delta t is defined as this. When t equal to when t is not 0, you get a 0 value. And when t is 0, you got an infinite value. And that's not the end of the definition. And then it also says if you integrate from negative infinite to positive infinite and integrate this delta t value, you get unit value 1. Okay. So let me explain this a little bit, and let's see how do we interpret this two-part expression in here. Okay, so here's what we can visualize this situation in here. Okay. Let's start with a box, and this box has a is a symmetric, and the bottom of the location edge and negative epsilon over 2 to positive epsilon over 2, and the height of it is 1 over epsilon. So you already this symbol here, okay, representing a very small quantity in mathematical notation. Okay, so what's the special part of the box then? Now, if I calculate the area of the box, if I calculate the area of the box, basically I will get the length of the bottom length and then multiply by the height. That give me the area of the box, right? So what's the area of the box? 1. Okay, yeah, very good. So essentially, so now I want you to visualize this. Okay, I'm going to let this epsilon approach 0. So make it as smaller and smaller and smaller. So what happens if I make it smaller, smaller, and smaller? So first, let's observe the two sides of the box. As epsilon getting smaller, then the two sides is shrinking and getting closer to 0, right? And this height, 1 over a very small number, is getting a very bigger number, bigger and bigger. So basically the box is becoming a much narrower but taller box, rectangular box. However, everything else, right, is still kept the same in terms of height and the two sides of the box. So then what happened if epsilon really becoming so small, approach limit concept approached to 0? Then literally you won't be able to see the two edges anymore, and then the box becomes essentially infinite. Okay. However, because this is a limit concept, right? However, what is the area of the box? It's still 1. Still 1. So basically, you don't see a box anymore. You just see an infinite bar there. But in your head, you still try to visualize that still a little bit of box there, right? And give me a total area of the box is 1. So that's basically what delta function, impulse function is. Good. So I want you to, this is, people sometimes remember this, but they forgot this one here. So you gotta, yes. Sorry, come again. A specific point on the graph. I use it to what? Sorry. Oh, okay, you're jumping ahead of me. Yes. So what do I use it for, right? Yes, excellent. Close. I do try to use it to try to pinpoint some values of uncertain graph. But you will see that this is actually what I'm going to cover today, right after this one. Okay, excellent. Okay, just a second. Let me. All right. Okay, so let's take a look at a few properties, and then we'll come to the idea presented by the students here. Okay, so first, a few comments, essentially looking at the few properties of this impulse function. So first comment, right? Let's get back to this idea when you integrate this impulse function, okay, from negative infinite to positive infinite, and you get a 1, right? Okay. But technically speaking, if you think about it, right? I mean, this is negative infinite. This is a positive infinite. Okay. Do I have to integrate from negative infinite to positive infinite? If let's say if my integral limit is actually somewhere here, like a to b, and a and b are on both sides of this vertical axis. So then, or in other words, your a and b like this, right? Okay. It naturally includes the box. Then the integral limits will still be 1, right? But remember, right now this epsilon is approaching to 0. It's a very, very limit concept. So this limit, suppose, right, you could just actually 0 minus to 0 plus. You recall that in your first year. Right? 0 plus 0 minus basically means it's somewhere right on the left of the 0, and it's somewhere right on the right of the side of the 0. Right? So that can still give me 1 in terms of this property here. Or even more loosely, right? This equal to 1 as long as this A and B contains 0. So that's the first property. Second property, right? If you look at the way the delta function is constructed, it started from basically a box out of here. Okay, so delta function is actually a even function. Even function basically means it's symmetric about the vertical axis. That basically can be identified using the starting point of this graph right here. There are many even functions, but delta is just one of that. Okay, good. So another thing is, because the area is equal to 1, okay, because this is equal to 1, we sometimes call this as it's a unit, right? It's a unit. So let's say, for example, let's say if I have a function, let's say k times delta t. Okay, k is a constant. So k is a constant here. So if you have a k times delta t, now let me ask a question. What is the area underneath k times delta t? Okay. So if I call this as a unit area, then k times delta t becomes multiple, right? K multiple of the unit. So this idea, right? So the area under k delta t is k. Good. So now let's move to another comment. Okay. So what if I multiply a function, say f of a t, with delta t, with an impulse? Okay, so we're getting there. Then what happens? So let's do that. Right. Let's say assume, of course, let's assume f of t is continuous at t equal to 0. Right? Okay, so we're multiplying f of t with delta t. So is there anything we could do, right, to simplify this? So let's go back to the delta t's definition. Delta t is defined as 0 when t is not 0, and when t is 0, there's an infinite value, right? So basically, delta t exists only at t equal to 0. So if I come to this multiplication at here, so that basically means it's going to be 0 when t is not 0. And when t is 0, okay. So technically, what do I get? When t is 0, then f of t becomes f of 0. And delta t, I don't need to change that. I can still keep it as a delta t, right? Because that's delta t itself. So when t is 0 is this. So if you look at the expression here, that means f of t times delta t basically can be written as f of 0 times delta t. So it's like we're getting to what the point is. It's like when you multiply a function with delta t, you're picking out, right? You're picking out the value at the t equal to 0, right? For the f of function. Okay. Now, if I get back to the previous comments at here, when you multiply constants with delta t, the area underneath this k delta t is k. So now, if I see this one here, there's no difference, right? So the area under f of 0 delta t is f of 0. Okay. So then maybe then you can naturally think about the question. Okay, so now you give, if I multiply f of t delta t, I pick out the value at f at the t equal to 0. And what if I want to pick out certain value at other locations, not just t equal to 0? Then what do I do? Yes. Shift which? Shift. Exactly. Right. So let's say you want f of a t at a location of capital T. Okay. Of course you can do this, but how do I pick it out? I can f of a t, right, times delta t minus capital T. So you shift the impulse function to a different location. And then you get f of a capital T times t minus delta t. Because this function in here, right? That's before. So then you get this is capital T here. You get an impulse at this location. And you multiply this impulse with any other function, you single out that value at the location. Okay. Excellent. Okay, and we'll extend from here a little bit more, and then we have a very important property called sampling property. Okay, right based on this one here. But let me show you another example here. Okay, so we're dealing with just generic f of t. So let's take a look at an actual function. Let's say I have a function e to the power of 2t, and then multiply by delta t minus 2. So here's the homework question. Simplify this expression. So now you can make use of the property out of here, because it's shifted t minus 2. So this basically become 2 times 2, and then delta t minus 2. You get e to the power 4, delta t minus 2. A little bit of twist. what would be this one? So what would be this one? Anybody? Well, let's hear a verb this time. Verb, yeah. What? Sorry. You still e to the power -4. Okay, so why? Yeah. Uh-huh. Hmm. You got it right, but you need a valid reason. What about you? Nothing from you. Okay. Yeah. Anybody know? Okay. So back. Yes. Going over the x-axis. Filling which function? I think if I understand correctly, you're trying to deal with this one, right? Yeah. Right. So you should use the right word. Remember what? Where did I see here? Oh, here. Delta function is an even function. Okay. So if it's an even function, then delta 2 minus t should be the same as what? T minus 2. Okay. Now you get the same results, as a matter of fact. All right. Okay. In the assignments, you have a few more exercise on this type of question. But the most important property is actually the next one. It's called sampling property. Okay, so sampling property says this. We are going to multiply the two functions f of t and delta t, and then we integrate from negative infinite to positive infinite. Okay. So let's see, what does this give us? Okay. So I'm going to make use of the results that we have derived. If I look at the integrand f of t times delta t, so that certainly can be rewritten as f of t, f of 0 times delta t. You're integrating respect to t, and this is a constant, so that can be taken out of the integrand, the integral, and you're left with just the integral of the impulse function. And we already know the impulse function is 1, so we left with just f of 0. So how the operation end up with, basically, when you do this, you end up with the single value f of 0. So this is a little bit different, right? In the previous case, when you multiply function with delta t, you still left with the impulse in the expression. But this time, you only have this original function value at t equals 0 over there. So that's called a sampling property, or something called a sifting property. You're only sifting out the one single value. And similarly, if I multiply f of t with delta t minus capital T, so shifted version of this impulse function, and take a wild guess, you should end up with f of capital T. Sifting out the value at t equal to capital T. So sampling property sometimes is also called a sifting property. Okay. questions on this part here? So right now, pretty much it's all about the definition of this impulse function here, right? So if you, let's say, if you're going to do a very specific example, so let's see, we are going to integrate e to the power negative 2t times delta t, like what we did. So then in this case, right, according to the formula, you are going to just replace the t with a 0 into the original function, exponential decay function, and then you end up with a 1. And if, let's say, we integrate a different function, so cosine pi t over 4 times delta t minus 2. Integrate this one. So basically, we're going to make use of the second property here, right? You have a shifted delta function. And shifted amount is capital T is 2. So we need to replace our t with 2. So t is 2, 2 pi over 4, pi over 2, cosine 90 degree, 0. Okay, so that's a few very useful applications of the sampling property. Okay. So if there's a quiz, oh, actually, by the way, I should say we're going to have a quiz next Monday. The other instructor is supposed to put up an announcement, but I guess he forgot. So we're going to have on Monday have a first quiz on system and signals. You know, basically the 3 properties, right? Probably you will have 2 questions, and you'll have 1 hour to do this quiz, and we'll open it for, let's say, 24 hours. Okay. See, Monday morning, 9 o'clock until 9 o'clock Tuesday morning. There should be plenty of time. And the type of questions, you know, since we're learning system signals, so you should expect a question to show the system is, for example, linear or time invariant. Right? Another type of question we demonstrated in assignments, also in the lecture, applications of the LTI system. So I have an input, and I give you the corresponding output, and tell you this is a LTI system, and then give you a different input, and ask you what would be the graph look like for the output. So you basically make use of the LTI property, right? So the first step, what do? You have to find the relationship between the new input and the original input. So then you can add or minus or even multiply, and then you get the output. Okay, so it should be straightforward, but you need to have a better, of course, understanding of the concept. It's all open. We also try to make it open, and you can discuss among yourself. There's a possibility that you get a different numbers. The question you get different numbers than your peer. So the point is, do not just copy each other, right? And then that would be very serious misconduct. All right, let's look at an example. This time, I'm going to do a convolution example. I'm going to convolute an arbitrary function f with delta t. Let's see what that gives us. Okay, so this part of the question, you know, I understand basically whenever you come to this kind of question, you probably would genuinely dislike this because it's all symbols, right? Yeah. But it's just had to get your brain used to these sort of things. Because the convolution, in the first step you do is you apply the definition of convolution. And that basically means f of tau, then multiply by t minus tau d tau. So then let's proceed from here. The rest of the steps mostly will be making use of the properties of impulse function. So for example, I'm going to make use of the even function property. So this t minus tau can be written as negative tau minus t. And because this is even, so then the negative sign can be taken out. So this step here, again, from here to here, we made use of the even property. Oh, actually, also, by the way, you're probably wondering, how come this is a negative infinite to positive infinite? Because remember, typically, when we do the convolution, what is the limit? 0 to t, right? And 0 to t, but if you recall, when we do the 0 to t, we assume this one is causal. Okay? So if it's causal, then definitely the integral limit is 0 to t. Okay? But if you relax the condition, basically, let's say if this is not a causal, then the integral limit will go from negative infinite to positive infinite. So let's continue from here. So now what happens next? So then we look at this multiplication here. Okay, look at the multiplication here. So you have to shift your gear a little bit, basically, which one is treated as being as a variable. So in this case, tau is becoming the variable now. And the t, you can consider temporarily as a quantity being shifted, right? So the delta function is a function tau, and then shift to the right by amount of a t. And then you multiply by function of tau, f of tau. So now you can make use of that property. That means I will only care about the value at tau equal to t. So replace it with the t here. And this is tau. So this integral is about dummy variable tau. Then f of t is relevant, is a constant, right, when it comes to this integral. So I can take the f of t out of this integral. And finally, what is the value of this delta function when you integrate from negative infinity to infinite? 1, exactly, right? Because negative infinity to positive infinity includes that delta function, doesn't matter where it is. So this is equal to 1, so then you end up with just f of t. All right, so now this essentially a property means if you convolute a function, arbitrary function, with an impulse function, then you end up doing nothing. You end up getting back to the function f of t. Okay. So similarly, if I'm going to convolute f of function with a shifted impulse function, shifted by capital T naught. So take a wild guess. What do you think you're going to get? F of t minus capital shifted word. Good. And that's fairly useful results that we may actually use it in some of our future work. Okay, so that's all about the impulse function. Okay, and the next lecture we're going to have a very important property of the impulse function when we apply it to a system. So basically, you give the impulse function as an input to a system. What happens? Right. But before we finish today, right? So now we learned the unit step function. We also learned the impulse function. So I wanted to connect the dots a little bit. Okay. What is the relationship between this unit step function and the impulse function? So this is not going to be a very rigorous math proof, but it will make sense. Okay, let's put this way. So let's start from this unit step function. The unit step function basically is a red curve. Okay, that's unit step function. So I want you to do, the next I want you to do is, let's take the derivative of the unit step function. Let's take derivative unit step function. So what does that gonna give us? Derivative basically means when you have a curve and you look at every location of the curve, derivative means it's a slope of that curve, right? So if I pick anywhere on the left side here, I mean, it's a flat. So the slope should be 0. If I pick anywhere over here, and the slope should be 0, right? So basically 0 when t is not 0. And at t equal to 0 location, so do you have a 90-degree of a jump? So what do you think the slope would be? Infinite, exactly, right? At the t equal to 0, you got an infinite slope. So what does this final results actually remind you? Which is delta t, isn't it, right? That's your impulse function definition. Okay, yeah. So that's a connection. If you take derivative of the unit step function, you get the delta function. Okay. Or if I do a reverse approach, if I'm going to integrate this delta function, okay, right? This is like a antiderivative. If you integrate this, you get 1 when this t is greater than 0 and 0 when t is less than 0. You will get back this unit step function. Okay. So let me give you a quick example here how you can actually interpret. For example, right? Let's say if I have a unit step function 2 times u of t minus 1. Okay. So if I graph this, this is a shifted unit step function. This is 1, and then the value of this is 2. Okay. Scale is not very up to scale. That's your unit step function. So what would be the derivative of this unit step function? What would be the derivative of this? Well, it's not exactly like the derivative of u of t, but it is still a derivative of this step function, right? So technically, you're not going to gain anything rather than the location t equal to 1. At the t equal to 1, you get a jump, but the unit of the jump, right, compared to the du over dt, it should be 2 times here. And it's also a shifted version of this delta t. And basically you can indicate what you typically can do is graphically you can indicate here you have a jump at a 1, and then you put a 2 over here to indicate the unit of that, right? Which means the area underneath that impulse function at here should be 2. Okay, so I'll go stop here in so 9:50, but I'll quickly give you an example and then we'll get on to the next important topic. Okay. Any questions? Feel free to come over, right? Yeah.